In the last video, I showed you how to find velocity information from a position versus time graph, so and how to get from there. And that was by using the slope at any given time. Okay, now I want to show you how to get from velocity to, it's really not going to position, but it's really trying to find the change in position. Okay, if I have a velocity versus time graph, and let's do it just like this. Okay, and let's just use, I don't know, 5, 10, 15. 5, 10, 15. If you go 15 meters per second for 10 seconds, well, we know velocity is displacement over time, right? So if you have a velocity, average velocity, and since this is constant, that is the average of 15 meters per second, and we have a time of 10 seconds, we have 15 equals delta x over t. And the t is 10 seconds, so delta x just ends up being 150 meters is the delta x. Well, look at this. 15 times 10, that's actually the area between there and there. That's kind of nice. I have no idea why my pen changed colors. So that area under the curve, I'm going to put area under a velocity versus time graph, gives you the displacement. Again, it tells you delta x. It doesn't tell you x because we don't know where it started. Something traveling 15 meters per second for 10 seconds, there's no information on the velocity graph of where we are. But we can tell how far we traveled. So this could correspond to, it's a constant velocity, so it could correspond to, I don't know, let's do -5, 0, 5, 10, 50. No, I can't do it because it's 150. I'm going to have to make them bigger. Let's make it 20, 40, 60, 80, 90, 100. 120, 140. Okay, so that could correspond to starting at -10 and going at a constant velocity over 10 seconds, right? Because this is 10 seconds here. So it traveled at a constant velocity for 10 seconds, and we know the difference was 150 from -10 up to 140, right? It could be that. It could be from 0 up to 150. It could be 80 up to 230. There are all sorts of lines that could correspond, but we were able to find the delta x, and that's the most important part. Don't care so much about finding the exact graph of position versus time from this, but I do want you to be able to find the delta x. We would have to know what its starting position is to do better than that. Okay, let's make a little harder problem. There we go. Let me erase this. And I'm going to move that graph a little bit, that velocity graph a little bit. How about this? Okay. Well, we got a little problem now. Because it's the area under the curve, 20, 25, 30. And that area under the curve, when I say the area under the curve, I mean area between, I'm going to put between graph and time axis. We call it the area under the curve, but as we're going to see, it's a little trickier than that. So the area between the graph and the time axis. So really what I'm doing is I'm going, because if I said area under the curve, I'd be filling in all this stuff down here. That's not right. No, we're just filling in the area between the graph and the time axis. And so that area, that's easy. It's a triangle. And we're going to use physical units. 1/2 base is 10 seconds times height. The height is 30 meters per second. You'll notice the seconds cancel. I didn't even do the units in the last one. 1/2 times 300 is, hey, look at that, 150. 150 meters. So it really doesn't matter that this was a different shape from that rectangle. They had the same area in the previous problem. And once again, all we can say is delta x equals 150. We can't really draw. It'll have a very, well, this one is speeding up. We can tell the shape is going to curve upward, right? Let me show you what I mean. Let me go from 20 up to 170. I think that's 170. Up here. Here we go. And I can just approximate it. I don't know for a fact. Let's just pretend if I told you the starting position was 20, I know the delta x is 150. I know it has to end up at 170. But I can tell a little bit more about the curve. Look at this. Down here, the velocity is 0. That's got to be pretty flat. The velocity gets higher. Therefore, the slope of the position versus time gets higher. I can actually do better than that, but I'm not going to bother with that. What I could do is I could say, oh, okay, after 4 seconds, what's that area? And then I could plot that, how much the delta x is from 20. And then I could do 6 seconds, and I can do 8, and so forth. But I'm not going to bother with that. I'm just trying to show you the concept. And now I'm going to show you one last little concept. And, you know, when you have these shapes, by the way, and I'll talk as I erase, when we have these shapes, just think of what does the shape remind you of. I'm not going to do this problem, but if you had this, well, you can break it down. You could break it down. You know how to find the area of a rectangle. You know how to find the area of a triangle. You add those together. But I'm going to do one harder thing here. And I am going to do, here's negative 10. I am going to do this. Whoops. Apparently I'm not going to do that. I'm going to select that again. There we go. Area between graph and time axis. Well, that's a little weird. Here it's below the time axis, so I would have to fill in, whoops, undo. I would have to fill in, oh, look what I've over undone. Let me drag this down again. Okay, so if I were going to fill this in, I'd have to fill it in that triangle. Remember, it's the area between the graph and the time axis. So it'd be 1/2 times 10 times negative 10. And we count this as negative because it's going in the negative direction the entire time. If you have a negative velocity, you're moving in the negative direction. So this is going to have to count as negative. Count negative. Okay, and that's going to be 1/2 times 10 times 10. Ooh, got times 10 times 10. That's going to be negative 50 meters is the displacement. Okay, and it can get even a little trickier, but just a little, because the basic rule I think you have now. Let me show you something. This is an actual, this comes up a fair amount. I throw a ball, what's called up positive. I throw a ball in the positive direction. This is not going to be the exact right numbers, but if you throw a ball up and it goes up and it comes down, it tends to have this kind of characteristic. Well, now we got to say for the first 5 seconds, that's the area. It was traveling in the positive direction all that time. So this displacement is going to, let me just draw it over here. So the displacement for the first 5 seconds is going to be 1/2 times 10 times 5 is 25 meters. Well, this ends up being the exact same for the next 5 seconds. Delta x is negative 25 meters. So the total displacement is 0. In other words, this area and this area cancel out. And you have 0 displacement. This happens a lot with, up and down motion. If I throw a ball up at 10 meters per second, the symmetry, the balance between the up and the down motions mean that, well, after that same number of seconds that it took going up, it's going to take that same number of seconds coming back to my hand, and I'll have a displacement of 0. It's back where it started. So what do you need to know really quickly? Slope of position versus time gives you velocity. Okay, area, and I'm going to say under v versus t, but we really mean between that and the time axis, gives you delta x, and that's an important thing, delta x. So you should be able to go back and forth between those. What we're ultimately going to have is this structure where you have position, velocity, acceleration, and the slope of position versus time gives you the velocity, slope of velocity versus time gives you acceleration, area under acceleration versus time gives you delta, change in v, area under velocity versus time gives you delta x. Okay, and at some point, once we get to acceleration, I'll actually talk about calculus for those of you that are taking calculus.